Hey everyone, and welcome to this explainer. If you're a grade 7 learner tackling physical science, you are in exactly the right place. Today, we're kicking off a brand new chapter, Unit 4, Lesson 1, all about wave properties. We're going to dive right into the fascinating world of waves and explore how they literally shape our reality. Think about it, from the light you're using to see this screen to the sound of my voice reaching your ears to the text you send your friends, it is all about waves. I am so excited to be your guide as we break down the fundamental science of how all this stuff actually works. Here is our roadmap for today. We'll be looking at the anatomy of waves, energy and amplitude, interacting with matter, analog versus digital, and finally, your transfer task. Let's jump right in. Every great scientific investigation starts with a big question, right? So keep this essential question in the back of your mind as we go. How do waves carry energy and information? Because whether we're talking about massive ocean waves crashing on a beach or the invisible Wi-Fi signals beaming videos straight to your phone, waves are basically nature's ultimate delivery system for both power and data. Section 1. The anatomy of waves. To understand how waves do all that heavy lifting, we first need to check out their repeating patterns. Let's start with our first key term, amplitude. This is the maximum distance a wave moves from its resting position. Picture a completely still, perfectly flat pool of water. That flat surface, that's the resting position. Now, imagine you drop a rock right in the middle, and a wave rises up. The distance from that flat resting position to the very top crest of the wave, that height is the amplitude. It's essentially a measure of the wave's overall intensity. Next up, we have wavelength. Simply put, this is the actual physical distance from one point on a wave to the exact same point on the next wave. So if you measure from the very top peak of one wave straight across to the very top peak of the next one, you've just measured the wavelength. It tells us how long one single complete wave cycle is in actual physical space. Our third structural property is frequency. Think of this as the countdown clock for the wave. Frequency is defined as the number of complete wave cycles that pass a specific point in a given amount of time. Imagine you're standing in one spot in the ocean, just counting how many waves hit you in exactly 1 minute. You'd be measuring the frequency of those water waves. It's absolutely crucial to understand the difference here. Wavelength is about how long a wave is in space, while frequency is all about how often that wave repeats over time. Now, we classify these repeating waves into two main categories: mechanical and electromagnetic. Mechanical waves absolutely need a medium to travel through, meaning some sort of physical matter like air or water. Sound is a perfect example of this. Electromagnetic waves, however, are a totally different story. Because light is not a matter wave, it doesn't need a medium at all. So while sound waves need matter to move through, light waves can travel across the absolute vacuum of empty space. That is exactly why we can see the brilliant light from the sun, but we can't hear the massive explosions happening on its surface. Moving on to Section 2, energy and amplitude. Let's connect that anatomy we just learned to some real-world power. Check out how these factors scale together in our worked example. Notice how when we have a low amplitude wave, we get low energy. Bump that amplitude up to medium, and the energy rises right along with it. And a high amplitude wave yields high energy. In science, we use mathematical representations exactly like this to prove that as the amplitude of a standard repeating wave increases, the amount of energy it carries scales up in a highly predictable way. So, to summarize this core concept, taller waves pack more power. This is a foundational rule in physical science. That predictable pattern is basically a secret code, telling us exactly how much energy a wave is packing just by looking at its height from the resting position. Bottom line, if you want to increase the energy in a wave model, you simply have to increase its amplitude. All right, Section 3, interacting with matter. We know waves travel, but what actually happens when they bump into stuff? Well, when a wave, like a light wave, hits an object, one of three things can happen, depending on the material and the wave's frequency. First, it can be reflected. That means it bounces right off the object, just like light hitting a mirror. Second, it can be absorbed, where the object simply takes the energy in. Or third, it can be transmitted, passing straight through the material. And here's a wild fact. When light is transmitted between different transparent materials, like moving from the air into a glass of water, the path of the light actually bends. So the next time you see a straw looking broken in a glass of water, you are literally witnessing wave transmission and bending in action. Section 4. Analog versus digital. How do we actually harness these wave properties to send a text message or an emoji? To answer that,
we really have to look at the two primary ways we encode information into waves. Analog signals are continuous waveforms. Think of an older radio or maybe a vinyl record flowing smoothly and constantly. Digitized signals, on the other hand, do not flow continuously. Instead, we break the information down and send it out in discrete, rapid-fire pulses of wave energy.
So why does most of our modern world run on digitized signals? Because of their absolute technical superiority. By sending data as precise wave pulses, we can easily convert binary patterns stored in our computers. This makes them highly reliable for encoding data. When you break data into pulses, like light pulses in a fiber optic cable or radio wave pulses in your Wi-Fi router, it becomes incredibly reliable for transmitting information, like texts, audio, and video over huge distances without losing the quality of the information.
And finally, Section 5, your transfer task. It's time to put you in the driver's seat to apply what we've just covered.
Here is your transfer task. Based on the wave properties we've explored today, I want you to answer this big question. Why are digitized signals a more reliable way to encode and transmit information? Think about how waves carry energy, how amplitude actually works, and the profound difference between those continuous waves and specific wave pulses. Use the evidence from this explainer to support your claim and argue the case for digital technology. Are you ready to convince someone that digital is the future? Good luck with your task. Keep looking for the science all around you, and I'll catch you in the next explainer.